Hello everyone. I'm just going to start recording me learning Rust. I didn't get too far into it, so I've already skipped the little hello part. I mean, I did it. And I'll probably be posting videos on my YouTube channel just to follow me along. I know I'm using Kate to load cargo, but it's fine, I guess, for right now. But right now we're on handling potential failure with result. And again, this is just going to be me going at my own pace and just kind of documenting what I'm doing. I don't plan to make very long recordings. They're not going to be cut down in any way. And they're just going to be me doing my own thing. So right now we're handling potential failure with result. Working on this line of code. We're now discussing a third line of text, but note that there is still a part of single logical line of code. Next part in this method, .expect failed to read line. We could have written this code as IO input output, stand in, read line, immutable guess, .expect failed. However, one line is too difficult to read, so it's best to divide it. It's often wise to introduce a new line and other white space to help break up long lines. When you call another method, call a method with the .method name syntax. Now let's discuss what this line does. As mentioned earlier, read line puts whatever the user enters into the string we pass it, but it also returns a result value. Result is an enumeration, often called an enum, which is a type that can only be in one multiple possible states. We call each possible state a variant. Chapter 6 will cover enums in more detail. The purpose of the results type is to encode error handling information. Results variants are OK and error. The OK variant indicates the operation was successful, and it contains the successfully generated value. The error variant means the operation failed, and it contains information about how or why the operation failed. Values of the result type, like values of any type, have methods defined on them. An instance of result has an expect method that you can call. If this instance of result is an error value, expect will cause the program to crash and display the message that you passed as an argument to expect. If the readLine method returns an error, it would likely be the result of coming from the underlying operating system. If this instance of result is an OK value, expect will return the value that OK is holding and return just value is holding and return just that value to you so that you can use it. In this case, that value is the number of bytes in the user input. If you don't call expect, the program will compile, but you'll get a warning. Unused result that must be used. This result may be an error variant, which should be handled. Hashtag warn unused must use on by default. Use let underscore equal result. Let guessing game then okay. I'm also installing a mod list right now. That's the main reason. I was looking for a Fallout New Vegas mod list. Hang on. I really don't know what I want to play. Probably. I mean, there's not a lot on here, are they? Oh, they're all unavailable right now. I might just play Begin again. Could play High and Dry. We'll play Begin again. Install mod list, Begin again. Should be fine. Start installation. Hang on, you can give me 1 second. Cat 1 then. Well, while this is running in the background, I guess we can continue. Rust warns you that you haven't used the result value returned from the read line, indicating that the program hasn't handled a possible error. The right way to suppress the warning is to actually write error handling code. But in our case, we just want to crash this program when a problem occurs. So we can use expect. You learn more about recovering from errors in Chapter 9. Printing values with println placeholders. Aside from closing curly brackets, there's only one more line to discuss in the code so far. Println, you guessed, guess. This line prints the string that now contains the user input. A set of curly brackets is a placeholder. Think of curly as little crab pincers holding a value in place. When printing the value of a variable, the variable name can go inside the curly brackets. So, variable guess, let mutable guess, string, so it's holding the variable guess and it's waiting for it to be inputted. Printing the result of evaluating an expression, placing the empty curly brackets in the format of a string, then following the format string with a comma separated list of expressions to print and each empty curly bracket placeholder in the same order. Printing a variable and then the result of an expression in one call to println would look like this. Let x equal 5, let y equal 10. Println x, and then x inside the variable is going to print out 5, and y plus 2 equal curly bracket. But so I guess this is taking okay, so this is not sure I follow this. I mean, I guess it prints off. I guess this goes out here. The code would print x equals 5 and y plus 2 equals 12, which it did. Learning the first part. Let's test the first part of the guessing game on cargo run. Please input a guess. Alright, you guessed. At this point, the first part of the game is done. We're getting input from the keyboard and then printing it. Next, we'll need to generate a secret number that the user will try to guess. The secret number should be different every time, so that the game is fun to play more than once. We'll use a random number between 1 and 100 so that the game isn't too difficult. Rust doesn't yet include a random number functionality in its standard library. However, the Rust team does provide a rand crate with said functionality. Increasing functionality with a crate. Remember that a crate is a collection of Rust source code files. The project we've been building is a binary crate, which is an executable. The rand crate is a library crate that contains code that is intended to be used in other programs and can't be executed on its own. Cargo's coordination of external crates is where Cargo really shines. Before we can write code that uses rand, we need to modify that cargo toml file to include rand crate as its dependency. Open that file now. Open the file now and add the following line to the bottom beneath the dependency section in cargo created for you. Be sure to specify rand exactly how we have here with this version, or the code examples in this tutorial may not work. We want rand equals 0.8.5 in the cargo toml file, everything that follows a header is a part of the section that continues. So header in dependencies, you tell cargo which external crate your project depends on and which versions of those crates you require. In this case, we'll specify the RAND crate with the semantic version specifier 0.8.5. Cargo understands systematic versioning, sometimes called SIM version, which is a standard for writing numbers, version numbers. Specifier 0.8.5 is actually shorthand for 0.8.5, which means any version that is at least 0.8.5 but below 0.9.0. Cargo considers these versions to have public APIs compatible with version 0.8.5. The specification ensures that you get the latest patch release that will still compile with the code in the chapter. Any version 0.9.0 or greater is not guaranteed to have the same API as what the following examples use. Now, without changing any of the code, let's build a project shown as listing. Cargo build. RAND 0.8.5 was used. You may see different version numbers. New one, yeah. You may see different version numbers, but they will all be compatible to code, thanks to Sulfur, and different lines depending on your operating system. The lines may be different in a different order. When we include an external dependency, Cargo fetches the latest version of everything that dependency is needed from the registry, which is a copy data from crates.io. Alright. Crates.io is where people in the Rust ecosystem post their open source Rust projects for others to use. After updating the registry, Cargo checks the dependency section and downloads any crates listed that are already downloaded. In this case, although we only listed RAN as a dependency, Cargo also grabbed other crates that RAN depends on to work. After downloading the crates, Rust compiles them and then compiles the project with the dependencies available. If you immediately run Cargo build without making any changes again, you will get the output then finished. Cargo knows it has already downloaded and compiled dependencies and you haven't changed anything about them in your Cargo toml file. Cargo also knows you haven't changed anything about your code, so it doesn't recompile that either. It will do nothing and simply exit 0 seconds. If you open the src main file and make a trivial change and then build it again, you'll only see 2 outputs. If we make this input your guess. How it compiled it. These lines show that Cargo only updates the build with your tiny change. So Cargo knows it can reuse what is already downloaded in the file for those. Ensuring reproducible builds. Cargo has a mechanism that ensures that you can rebuild the same artifact every time you or anyone else builds your code. Cargo will use only the versions of the dependencies you specified until you indicate otherwise. For example, say the next week version 0.8.6 of RAND crate comes out, and that version contains an important bug fix, but it also contains a regression that will break your code. To handle this, Rust creates the cargo lock file the first time you run Cargo build. So now that we have this in the guessing git directory. Cargo lock. Okay. Cargo has a mechanism. When you build a project for the first time, Cargo figures out all the versions of the dependencies that fit the criteria, and then writes them to cargo.lock file. When you build your project in the future, Cargo will see that the cargo lock file exists and will use the version specified there, then rather than doing all the work figuring out what versions again. This lets you have a reproducible build automatically. In other words, your project will remain 0.8.5 until you explicitly upgrade. Thanks to cargo.log file. Because the cargo.log file is important for reproducible builds, it is often checked into source control with the rest of the code in your project. Updating crate to get a new version. When you do want to update a crate, Cargo provides the command update, which will ignore the cargo.log file and figure out the latest versions that fit your specifications. Cargo and the cargo.toml. Cargo will then write those versions in the cargo log file. Otherwise, by default, Cargo will only look for versions greater than 0.8.5 and less than 0.9.0. If the RAN crate has released then two new versions, 0.8.6 and 0.9.0, you would see the following. If you ran Cargo, Cargo ignores the 0.9 release. At this point, you would also notice a change in your cargo.log file, notating that the version of the RAN crate you are now using is 0.8.6. To use RAN version 0.9 or any other versions in the 2.9.x series, you'd have to update the cargo.toml file to look like something like this instead. Next time you run cargo.build or cargo build, Cargo will update the registry of the crates available and reevaluate the RAN requirements according to the version you have specified. There's a lot more to say about Cargo and its ecosystem, which we'll discuss in chapter 14, but for now, that's all you need to know. Cargo makes it very easy to reuse libraries, so crustaceans, I guess, are able to write smaller projects that are assembled from a number of packages. Generating a random number. Let's start using RAN to generate a number to guess. The next step is to update our src main file, as shown in the listing. So, we're going to add use RAN RNG, and then we're going to let secret underscore number equal RAN thread underscore RNG dot gen underscore range. So it's going to RNG under the range of 1.100. I guess this is 1, 2, 3, 4, and so on. Print ln. The secret number is, and then these squiggly lines, secret underscore number. Print input your guess. Let much guess mutable. Print you guessed ln. Let's just do cargo build. Cargo run. Secret number is 35. We do it again. 32. 15. First, we add the line use rand, and we're calling the rand and the RNG trait. Defines methods that random number generators implement, and this trait must be in the scope for us to use those methods. Chapter 10 will cover those traits in details. Next, we're adding two lines in the middle. In the first line, we call the ran thread RNG function. That gives us a particular random number generator that we're going to use. One that is local to the current thread of the execution and is seeded by the operating system. Then we call the genRange method on the random number generator. This method is defined by the RNG trait that we brought into the scope. With the useRand RNG statement, the genRange method takes a range expression as an argument and generates a random number in the range. The kind of range expression we're using here takes the form start ... equals end and is inclusive on the lower and upper bounds. So we need to specify 1 ... so etc. to 100 to request a number between 1 and 100. You won't just know which traits to use and which methods and functions to call from a crate. So each crate has documentations with instructions for using it. Another neat feature of Cargo is running the cargo docs-open command. We'll build documentation provided by all your dependencies locally and open it in your browser. If you're interested in other functionalities, for example, then click the RAND in the sidebar. Cargo doc-open. Oh. RAND. Okay. Red RNG. Change rate, integer 32. Cool. I actually did not know to do that. The second new line prints a secret number, and this is useful while we're developing the program to be able to test it, but we'll delete it from the final version. It's not much of a gain if the program prints it as soon as it starts. Try running a few times, which I did up here. You get random numbers generated all between 1 and 100. Great job. Comparing the guess to the secret number. Now that we have the user input and random number, we can compare them. The step is to show in listings 2-4. Note that this code won't compile just yet, as we will explain. So we need, I'm going to put a new line at the top. Use std cmp ordering I guess it's just snipping the top part so that way we can see the rest of this. Match guess CMP. No idea what CMP stands for. God, I need to really learn my damn keyboard. Number. Ordering. Less equal. Rent ln. Too small. Okay, so we're going to do 3. Ordering greater rent ln too big. Ordering equal rent ln. You win. We forgot the commas. First, we'll add another use statement, bringing a type called std_cmp ordering into the scope from the standard library. The ordering type is another enumeration, and has the variance less, greater than, or in equal. These are the 3 outcomes that are possible when you compare 2 values. Then we add 5 new lines at the bottom that use ordering type. The CMP method compares 2 values and can be called on anything that can be compared. It takes a reference to whatever you want to compare with. Here it's taking guess and then comparing it to secret number. Then it will return the variant of ordering enum we brought into the scope. With the use statement, we use a match expression to decide what to do next based on which variant of ordering was returned from the call to CMP, with the values and guess and secret number. A match expression is made up of arms. An arm consists of a pattern to match against, and the code that should be run if the value given to match fits the arm pattern. Rust takes the value given to match, looks through each arm's pattern and to match. Looks through each arm pattern in turn. So I guess these are the arms. Yes, patterns, and the match constructs powerful Rust features. They let you express a variety of situations your code might encounter, and they make sure you handle them all. These features will be covered in details in Chapter 6 and Chapter 19 respectively. Let's walk through the example with the match expression we use here. Say the user has guessed 50 and the randomly number generated here is 38. The code compares guess 50 to the secret number being 38. The CMP method will return order greater because 50 is greater than 38. The match expression gets the ordering greater value and starts checking each arm pattern. If it looks at the first arms pattern, ordering less, and sees that the value ordering greater does not match ordering less. So it ignores the code in that arm and moves on to the next arm. The arms pattern is ordering greater, which does match ordering greater. The associated code in the arm will be execute and print too big to the screen. The match expression ends after each first successful match, so it won't look at the last arm in this scenario. However, the code in listing 2.4 won't compile yet. Let's try. Mismatch types, secret number, and arguments to this method are incorrect. Found and was expecting. So does it want what does it want the secret number like to be when I make this? Maybe I'm overthinking. Yes, because I am. Oh, it's expecting an integer. Oh, and we'll read the code. I'm not sure. The core of the error states that there are mismatch types. Rust has a strong static type system. However, it also has a type interface. When we wrote let mut guess equal string new, Rust was able to infer that guess should be a string, and it didn't make us write the type. The secret number, on the other hand, is a number type. A few of Rust number types can have a value between 1 and 100. I32 is a 32-bit integer number. U32 is a unsigned 32-bit integer, 32-bit number. I64 is a 64-bit number, as well as others. Unless otherwise specified, Rust defaults to an I32, which is the type of secret number unless you add the type information elsewhere. That would cause Rust to infer a different numerical type. The reason for the error is Rust cannot compare a string and a number type. Ultimately, we'll want to convert the string the program reads as an input into a number type. So that way we can compare it numerically to the secret number. We do so by adding the line to the main function. Let mut guess. And then I guess we are doing let's guess. Why is this? I guess U32 equal s.trim dot phrase dot expect. Please type a number. The line is let guess 32. We create a variable named guess, but wait, doesn't the program already have a variable named guess? Well, it's mutable, right? Let mutable. Helpfully, Rust allows us to shadow the previous value of the guess with a new one. Shadowing lets us reuse the guess variable name rather than forcing us to create two unique variables, such as guess str and guess. For each example, we'll cover this in more detail in Chapter 3, but for now, know that this is a feature often used when you want to convert a variable from one type to another type. We bind this new variable to the expression guess.trim phrase. The guess in the method in the expression refers to original guess variable that contained the input as a string. the trim method on a string instance will eliminate any white space at the beginning and end, but you must do so before converting the string to a U32, unsigned 32 number, which can only contain numerical data. Nope, it's New Year's. Happy New Year's, guys. Ooh, 2026. I'm shooting off fireworks. Which can only contain numerical data. The user must enter to satisfy read line to input the guess, which adds a new line character to the string. For example, if the user types 5 and presses enter, guess looks like this. 5/n interprets new line. On Windows, pressing enter results in a carriage return and a new line. /r/n. The trim method limits the n or /r/n resulting in just 5. The phrase method on strings converts a string to another type. Here we use it to convert from a string to a number. We need to tell Rust the exact number types we want by using letGuess 32-bit. The colon after guess tells Rust will annotate the variable type. Rust has a few built-in number types. U32, seen here as unsigned 32-bit integer. It's a good default for a small positive number. You'll learn more about the new number types in Chapter 3. Additionally, the U32 annotation in this example program in comparison with secret number means that Rust will infer that secret number should also be a U32. So now the comparison will be between two values of the same type. The phrase method only works in characters that can logically be converted into numbers, and so can easily cause errors. If, for example, the string method contained a thumbs up and percentage, there would be no way to convert that to a number because it might fail. The phrase method returns a result type much as the readline method does. Discussed earlier in handling potential failure result. We'll treat this result the same way by using the expect method again. If phrase returns an error result variant because it couldn't create a number from the string, the expect call will crash the game and print the message we give it. If phrase can successfully convert the string to a number, it will result the OK variant of result, and expect will return the number that we want from the OK value. Now let's run the program now. You win. Well, I was guessing. I was going off this one. You guessed 76, and I guess happened to just be 76. Nice. Even though spaces were adding before the guess, the program still figured out the user guessed 76. Run the program a few times to verify the behavior. Five. Please type a number. Let's change it by adding a loop. Private secret number. What? I'm confused. Oh, we add the loop. Please input your guess. So I guess we take loop. I guess I'll just do this. Now I need to probably use VS Codium at some point. We want this guy out of the loop. How if we run 99, 99, 55, 100. Oh, I've got 100. As you can see, we moved everything from the guess input prompt onwards into a loop. Be sure to indent the lines inside the loop another 4 spaces each and run the program. Again, the program will now ask for another guess forever, which actually introduces a new problem. Oh, that's right, it does not quit. User could always use Control-C, but there's another way to escape this insatiable monster. As mentioned in the phrase discussion, if the user enters a non-numbered will take advantage. So I'm quit right here. Typing quit will crash the game. You know, so we'll enter any other non-number input. This is suboptimal to say the least. We want the game to also stop when the correct number is guessed. Let's program to add a break. So, okay. We want you win. But we're gonna continue it with print ln you win. That's you whine. Continue with break, and break should always stop the code from functioning. So now if we run cargo. Ooh. Oh. Probably should have like ended this part. To further refine the game's behavior rather than crashing the program when the user inputs a non-number, let's make the game ignore a non-number so the user can continue guessing. We can do that by simply altering the line where guess is converted from string to U32. This should probably also be so instead we're going to what? Where did please type a number go? So what? We're removing. So okay, so we're making let guess equal let guess 32 equal match guess dot trim any of the white space and phrase it. Okay. Oh, okay. Noon equal noon error. Continue. We switch from an expect call to match expression to move from crashing on an error to handling the error. Remember that phrase returns a result type, and result is an enum that has the variance OK and error. We're using match expression here as we did with the ordering result of the CMP method. If phrase is able to successfully turn that string into a number, it will return an OK value that contains the resultant number. That OK value will match the first arm's pattern, and the match expression will return the num value that phrase produced and put inside the OK value. Number will end will end up right where we want it in the new guess variable we're creating. If phrase is not able to turn the string into a number, it will result in an error that contains more information about the error. The error value does not match the OK enum pattern in the first match arm, but it does match the error pattern in the second arm. The underscore is a catch-all value. In this example, we're saying we want to match all error values no matter what information they have inside of them. So the program will execute the second arm's code. Continue, which tells the program to the next iteration of the loop and ask for another guess. So effectively, program ignores all errors that phrase they might encounter. So now if you run, huh? What? Okay, it's fine. I'm confused. Why is it? Huh? What? Huh? What the fuck was different about it? I spelled continue wrong? What? Oh, no, because I'm so confused. How is unused? What? Okay, well, I can see that this is also here, but I don't. What's different about it? Okay. Let me read this, I guess. Ordering. Use rand. Function guest number. Let secret number range print. Hello, secret number. Please input your guest. Oh, this is up one. Let mutability guess equal string. Dot read line. Fail to read line. Let guess. 32 match guess. Oh, I missed a dot. Is this all that was missed? Nope. What? Huh? Period. Uh-huh. I'm so fucking confused. I spelled it wrong. Man, I sure am a G. I spelled it wrong. Catch all variable. Everything should work. Cargo, 42, 48, or 46, 45. You win. Bah, 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 bah. Boom, boom. I don't even know what it was. Oh, 47, oh, 46. Awesome. With one tiny found tweak, we'll finish the guessing game. Recall that the program is still printing out a secret number. That worked well for testing, but it ruins the game. Delete the print ln code. At this point, successfully built the game. 55, 33. 15, 22, 20. There's 20. So now we are at the start of chapter 3. I'm gonna stop for now. Man, I spent 45 minutes. So like I said, this is just kind of just gonna be me going through, just learning how to code in Rust. Because I do know some people do not like AI used at all in coding, and I understand, and I'd like to at least show that I'm trying to learn how to code in the meantime while I'm still working on my project. So thank you and have a happy new year, guys.